buff, I'm going to present you the first running distributed MILS system that we have here at Fortis. So first I'm gonna show you a small example, and then I'm gonna show you how the hardware is implemented here, how we can configure it, and how we can run the example on this particular hardware. So here is our example. We have two subjects. One that we call L for low security is connected to a camera, and the camera has a driver which we do not trust because it's distributed by a third party and we don't know exactly what it does. And then we have a subject that we trust, which we call H for high security, and this subject hosts an object recognition algorithm. In order to drive these two subjects, we have two additional subjects, namely D for dispatch and U for user. So the user sends commands to L and H and can also switch between modes. So whenever the user sends the switch L message, it means that it switches to low security mode and the next commands have to be forwarded to the low security mode. So for instance, it can use switch to L to say that he wants send the command to the low security subject, and this command will be something like take a picture. Then the picture is forwarded to the high security level subject. Then the user will switch to the high security, so send the switch H message, and ask the user to recognize a particular object on the picture. The command then will be forwarded to the high level user, and the results will be forwarded to the user. So this application is inspired from the Van der Meyden Starlight example from one of its papers. The example actually comes from an Australian defense project that was used to allow the soldiers to go on the internet while still working on high security stuff. So now that we have this example defined, we want to ensure some security property on it. So in the previous behavior, we see that the user asks the high-level subjects to recognize some objects, and we don't want that the low-level security subject is able to know what these objects are. So in order to ensure this guarantee, we have an argument that is built on two main points. So first, the communication between the subjects is restricted by the platform configuration. So here, a subject can send a message to another one only if there is an arrow between them. So for instance, here, L cannot send a message directly to you. And then we ensure that the dispatch component that is doing the switching work here send only commands to the right subject according to the current security mode. So this behavior can be described by an LTL formula that is written here and can be then checked using a model checker such as a new SMV. Our platform is as follows. We have two nodes that are connected through a switch. So the switch is a time-triggered switch, which allows us to have a deterministic network, meaning that we know that the packet will always be arrived and will always arrive at a specific time. Furthermore, we know that if a packet arrives, it comes from an identified sender and it cannot be sent by anybody else in the network. So now to deploy our example on this platform, we have to make some choices to know where to deploy each subject. So we did the following choice. H and L have been deployed on node 1, and D and U have been deployed on node 2. So now I will show how we can configure the network by configuring the switch, and how we can run concurrently the two subjects on each machine by configuring the separation kernel. And then I will show the example running, and finally I will try to do some very basics attacks on that switch and from inside the subjects in order to see whether we can get some information from an attacker point of view. Now we are going to configure the switch. For that we have a software which is based on Eclipse and in which we can set different parameters. So for instance here we can set the parameters relative to the switch. And once we have configured the switch and generated a configuration, we can plug the network. Yes. Then we can use another tool where we can choose the configuration that we generated, and we can simply load it into the switch, which will first erase the existing configuration and load the new one. Now we are going to configure the separation kernel running in each of the nodes. So in order to do that, we have a script that will assign some resources to each subject in each node. So on the first node, remember that there is two subjects. There is the low subject, which is called L, and the high subject. So here on this configuration file, we can see that these two subjects are here. So there is FE1, which is high, and FE2, which is low. And some resources are allocated to them. So for instance, we have here some memory. Here we have a partition of the hard drive. And here we have some network cards. So there is one network card that is used directly for communicating with the other subject. So this one is directly plugged to FE2, which is the other subject. And there is another one that is a remotely addressable object, so which is used for communication with the time-triggered Ethernet network. And we have pretty much the same thing for the second node, so which is called TT2. Now we will simply run this tool, this configuration file. We'll see that it generates some files, so XML files that basically are a more precise description of the configuration, and a SRP file that is the image that will be used to boot the machine. So there are two images. There is a TT1 that is for booting the first node, and TT2 for booting the second node. So then we have on the platform a TFTP server. So here, and on the TFTP server, we have this SRP file that are used to boot the machine via the network. So now that we have configured our boot server, we need to connect the regular Ethernet card of the first node to this port, which is configured. So in order to allow the system to boot via the network. So let me explain quickly how this works for the switch. These two cables here are connected to the time-triggered Ethernet cards. These ports are used to connect the regular Ethernet cards. So now, when we start the node, it will try to boot through the network using this part, and it will try to find the TFTP server. So now it's looking for the TFTP server, and now it found it, and it's logging the image that we just generated. And now this is the booting of the hypervisor. And finally, this is the booting of the first subject. So now the system is booted and it's working. We can see that the time-trigger network is active because there is the blink for the synchronization. And what we can do is that we can now completely remove this cable because they were used only for booting. So we don't need them anymore, and we can just leave the switch where the only connection is the time-triggered Ethernet network. So now that the system is booted and works, we have launched the applications in each of the subjects. I have the two nodes here. This is the first node, which runs the low and high subject, and this is the second node, which runs the user and the dispatch. So with the features of the hypervisor, I can switch between the subjects like this. So for instance, here I'm in the user and I'm asked for a command to type, and I can move here to the dispatch. So here, for instance, what I can do is switch to low security mode, and then the dispatch will detect that I want to switch to low security mode. And now here I have the low security subject, the one with the camera. So if I send a picture now, since I've just switched to low security mode, it will go directly to the low level subject. So if I ask to take a picture, then we see here that is executing the command another time, and here we receive a confirmation that the command has been received, and this confirmation actually goes through the high subject, as we can see it here. We forward the results. And now, if we want to go further, we can switch back to the high security mode. So switch to high, and ask to find, for instance, the black hats that are on the picture. And here we'll see that the command is executed here on the I subject. We receive confirmation that the command has been executed, and on this low-level subject we don't see anything because we are not supposed to know that there has been a command sent to the high level. Now we have plugged an attacker computer into the switch, and we want to see what information we can get from here, so we will use a standard sniffing tool that will capture some packets. So here we see that nothing is happening actually, and some packets arrive, but these are all packets sent from the computer, so if we apply a filter, we remove them, and we don't see that, except the packets outgoing from this computer, there is no incoming packet. So the second step is to try to flood the switch, and for that we use a standard tool from the dsniff package, which is called MacOF, and we say that it's on the first Ethernet card that we want to do this attack, and then we load it. And it basically sends a lot of wrong MAC addresses to overflow the cache in the switch. So despite the flooding attack, the switch is still working and we are still able to transmit commands from one computer to the other. So now we are inside the low-level security subject, which is potential attacker. So let's see what he can learn from the network. So this is the same software as the previous one, but here it's a text pod, and we try to see what packets we can get. So here there is nothing, of course. Now we can try to send some commands over the network to see if there is some information, and we see that here we are sending and receiving commands, but this guy is not aware that there is anything going on. So we can try, as for the other one, we can try to do a MAC overflow attack. So we'll basically run it again. And so the low subject is overflowing the network with bad requests. And we can see here that the network still works. So if we switch back to the high subject here, we see that whenever we send the command, it's executed here, so the application still works. So as you can see, we're being attacked from the inside and the outside, but our application is still fully working without any interruption. I really hope that I could demonstrate to you that the MILS platform is suitable for developing mixed criticality embedded systems.
Perfect. Good.